Picture this, walking into a smart home where the lights gently fade up instead of blasting at full brightness, the ceiling fan adjusts speed smoothly as the temperature rises, and blinds tilt precisely to block sunlight. None of that would be possible if the ESP32 could only turn things fully on or off. The trick is pulse width modulation, or PWM. It doesn't generate real analog voltage, but by rapidly switching a pin on and off at just the right ratio, it convinces LEDs, motors, and servos to behave as if they're under fine-grained analog control. In this lesson, you learn how to harness PWM to adjust LED brightness, regulate fan speed, and control servos with precision, skills you'll use in virtually every automation project. Think of PWM as slicing time into tiny windows. In each cycle, the pin is high for a fraction of the time and low for the rest. That fraction, the duty cycle, controls how much energy the device feels. At 25% duty cycle, an LED looks dim. At 50%, it's half bright. At 100%, it's fully on. The frequency is equally important. Too low, and LEDs flicker. Too high, and servos won't respond correctly. On the ESP32, you configure PWM using channels and timers so multiple actuators can each get the right mix of frequency and duty cycle. The magic is that while the microcontroller is rapidly toggling, your eye or the motor's inertia smooths it into a continuous effect. Here's a practical cheat sheet I've built from years of trial and error. LEDs behave best between 500 and 1000 Hz. Below that, human eyes start noticing flicker. Servo motors demand a much slower, fixed frequency around 50 Hz because their internal circuits expect precise pulse widths. DC motors and fans prefer several kHz, where noise is less noticeable and speed is smoother. Choosing the wrong range is one of the most common mistakes beginners make, like running a servo at 1 kHz and wondering why it jitters uncontrollably. This table should become part of your design toolkit whenever you're setting up PWM. Let's start with a simple LED to see PWM in action. Imagine GPIO 5 wired through a resistor to an LED. By attaching that pin to a PWM channel, setting a frequency of 1 kHz, and sweeping the duty cycle from 0 to 255, you'll see the LED gently fade in and out. What's happening behind the scenes is the pin toggling thousands of times per second, but the LED's persistence makes it appear to glow smoothly. Try it, and if the light seems to step instead of fade, check your resolution setting. You probably mismatch the duty cycle values with the configured resolution. LEDs are forgiving, but servos are picky. A servo expects a control pulse about every 20 milliseconds, where the high duration tells it the angle. 1 millisecond means 0 degrees, 1.5 milliseconds is roughly 90, and 2 milliseconds gets you near 180. Anything outside that range and the servo either twitches or stalls. On the ESP32, libraries like ESP32 Servo handle these timings for you. But it helps to understand the physics. The motor's internal circuit is literally measuring pulse widths. When powering a servo, always consider its appetite for current. Hooking it straight to the ESP32's 5V pin is a rookie mistake that leads to resets and jitter. Use an external supply and tie the grounds together. Over the years, I've seen the same mistakes crop up again and again. The most frequent is forgetting to connect the servo's ground to the ESP32's ground. The control signal simply won't register. Another classic issue is LEDs that seem to jump brightness instead of fading. That usually means your resolution and duty values don't match. Servo jitter often comes down to noisy power rails, which you can calm with a capacitor across VCC and GND. And if your board resets when you move a servo, you're probably pulling too much current from the ESP32's regulator. Give the servo its own supply. Keep these in mind, and you'll save yourself hours of head scratching. Once you've mastered LED fading and servo sweeps, it's time to put PWM into meaningful use cases. Try building a smart night lamp. Combine an LDR input with PWM so the LED automatically dims when the room is bright and glows softly at night. Or design a temperature-controlled fan using a DHT11 sensor, mapping temperature to fan speed via PWM. A more advanced challenge is servo-controlled blinds that tilt based on sunlight levels. Each of these projects combines input, processing, and PWM-driven output, turning raw knowledge into actual automation. The skill you're developing here is not just PWM itself, but integrating it into feedback loops that make IoT devices adaptive. PWM is one of those fundamental techniques you'll use constantly in IoT projects. You've learned how duty cycle and frequency shape actuator behavior, how LEDs, DC motors, and servos each have their own requirements, and how to avoid common mistakes like mismatched resolutions or unstable power. More importantly, you now know how to take PWM beyond simple demos and apply it to adaptive automation where actuators respond intelligently to sensors. Mastering PWM moves you from just switching things on and off to giving your projects the smooth, human-friendly control that defines modern IoT systems.